Hello class, this is chapter 3 on probability and sampling. The concept of probability is very important in statistics. When we collect data from a sample to learn about a population, it's a very important concept, as well as especially when we test hypothesis using the data that we collect. Consider an example of tossing a coin and getting 3 heads in a row. This is an example from your text. And as you can see, what you're going to do to figure out the probability of that is you list all the possible outcomes right here in this table. And as you can see, the probability of heads, heads, heads is 1 of 8 possible outcomes. And so you'll divide 1 divided by 8, and you'll get 12.5%. So the chance of that is 12.5%. And the important thing there is to take a look at each possible outcome is going to be determining a certain percentage. So you can take a look at that and compare it to the total and determine the percentage of each possible outcome. Why is that important? Because you'll see that we use this in statistics quite often. We can determine the probability of any results in our data by kind of same thing we're talking about just with the tossing of the coin. Considering the total number of possible outcomes and then calculating the proportion of those outcomes that correspond with our outcome of interest. This process can be used to consider the likelihood of obtaining a specific sample mean from a specific population. For example, in the chart below, what is the likelihood of obtaining a sample with a mean of 115? So as you can see here, if this is the distribution of sample means, which you learned about in your chapter, and most of the scores are hovering obviously around 100. Let's say it's some test that people can achieve, you know, the top score of 115 or something like that, and 85. And you drew, let's say there's 100 samples total of whatever number that you want to say, and then you drew one of the samples from those possible 100 samples, and their scores were 115. What would you say the how many instances of scores 115 in the population are there? So obviously it's not 50, right? Because if there were 50 out of 100, that would be the exact middle. So might there be 25 of those scores that are in this distribution right here? Probably not. That's probably going to be right here. If you looked at the total number of scores, and you can see the frequency of number of scores, the majority of them are obviously in the middle, and then they tail off here in this symmetrical distribution. But you can see the majority of the scores are here, but 115, not too many scores, right? You know, we could probably say that out of these 3 choices, the majority the scores of 115, there's probably only around 2 or maybe 1 score out of those 100, right? And so what percentage of that? That's 2 out of 100. That would be 2% would be the correct answer there. And this example shows us 2 things. It shows us the potential for sample error. If there's 100 potential samples out there and we draw one that is, our sample mean is 115 versus hovering close to here, that's quite rare, wouldn't you agree? As you can see, there's not too many instances of 115. There's not too many instances of 85, but there's quite a few scores that are hovering within this area. And we can say with a percentage how many of surety, right? How many scores are going to hover kind of between here or hover just within 115, right? Because it's the number of instances out of 100, right? In the example, just like the tossing of the coin, okay? So right there, what did we say? Probably 2% or less, okay? So there's a potential, this example shows us potential for 2 things. The potential, obviously, for sample error. Let's say you decided to take a sample and test these participants, and you found that they scored really high on this. But let's say, even though you did really great sampling techniques, let's say for some reason a bus of Mensa students showed up at McDonald's where you were testing on this caffeine study or something like that. And you know, you were randomly selecting people that entered into McDonald's throughout the day, but there was a Mensa, I don't know, conference nearby, and they all liked McDonald's or something like that. You know, not very likely, right? But it could happen, right? But it would be a very few instance of that in this theory. And this is a theoretical theory, right, of the distribution of sample means. And we'll use this theory to justify how we say if an experiment is significantly different, our results are significantly different from a control group, like let's say comparing the caffeine group to the placebo or non-caffeinated people. In this instance, we're talking about potential for sample error. Testing the whole population, right, is not practical. So we test a portion of the population. Choosing one sample among 100 possible samples can give us different results than below, though. As we increase, or can give us different results, as you can see from below. As we increase the number of samples, however, it becomes more and more like the population curve below. So let's say we tested one sample and we got 115, but then as we test more and more samples when we get towards 100, what are we going to find? That they're going to all look like this, right? So as you can see, just choosing one sample, you could get something over here. You more than likely could get something over here, right? Based on our percentages and the distribution of what you're going to find. So as you can see, as we increase the number of samples, it becomes more and more like the population curve below, right? If you just chose one, it might more than likely will be here, but as you choose more and more, you're going to see this distribution because one, and then as you get up to 100, it's going to look exactly like the 100, right? So as you see, as we increase the number of samples, it becomes more like population curve below. So as you'll see in future chapters, when testing, we must use an adjuster, which is called the sample error, or standard error, estimated standard error. And this uses a sample size to adjust for the possibility of sample error. But as I just indicated right up above, this adjuster, as you'll see, diminishes as we increase our sample size, because as our sample size, or the number of samples that we obtain, we get more and more. What does it do? It looks more and more like the population, so we don't have to worry about sample error. So the distribution of sample means also tells us something important in terms of statistics about probability and hypothesis testing. What do I mean by that? We can use probability and hypothesis testing by reviewing the results of our experiment against a control group. So we talked about the caffeine people and the control group, the placebo. We use the control group as our population or baseline, if you will. So this is the control group, the way it looks. And we compare our mean scores for the caffeine group to the control. So let's say our caffeine group, we did great sampling, and so we don't have to worry about sampling error because we did great sampling, or don't have to worry as much, right? And we had a really big sample size, let's say, in this experiment, so we don't have to worry as much about sampling error. So then you'd say, well, what is the likelihood of getting a score of 115, right? Way over here. And remember what we determined that was? Not very likely, right? Okay. If there is a sample, if the sample and the population were the same at the start of the experiment, and that's what we assume, right? We've created all the conditions, we've controlled all the conditions. So basically, we've randomly assigned the participants, and we've used a big sample size. And so we basically are assuming that they're going to be the same. But then we give them something, right, that's going to differentiate them. We give the experimental group one thing that's different, right? We give them caffeine. And so now they can become different in some way, even though we're assuming they were at the start of the experiment, they were the same. So then going back to what is the likelihood of getting a score of 115 if the sample and the population are the same at the start of the experiment? It is 2% or less, right? Not very likely that we got that. Okay? So we can say something from that. We can then extrapolate and say that the chance of getting these results based on error alone is 2% or less, right? Most of the scores should be near 100. But we don't want to say the chance of getting, or talk about the caffeine group, the experimental group, in terms of error. We want to talk about how sure we are that these were based on some difference, right? Our caffeine. Using inferential statistics is what we're going to do. We use things like the mean, variability, and sample size, which this the first couple chapters kind of touched on, but your future chapters are going to talk more about the mean and variability. Did talk about sample size. We can then say that our results, that we got 115 for this group versus the control group. support our hypothesis that the caffeine improves memory, and with what? A 98% surety or a 2% chance of error. So hopefully that makes sense in terms of that distribution, probability, and then extrapolating and saying we can say with a surety this probability in terms of the differences between the groups. I don't think the book really made it that clear, but hopefully that does. And skipped on. Okay, so then this just talks about in the book about this is the population as a dartboard, and each individual score is a dart, if you will. And they didn't really talk about it, but I think that the way to extrapolate this is not only is the population a dartboard, but the middle is where they all hover. Not how many scores you're going to get per se, or the difference between 20 and 1 and stuff if you're playing darts for that type of thing where you're trying to get a lot of points, right? So I think it has to do with this. And what you would find in this dartboard, right, is where they're all going to hover. Most of the darts is going to be in the population in the middle. And then as you get out to more outliers, if you will, those are the more random or variable scores, they're going to be less, okay? But as you can see, when we choose an individual from the population to observe their behavior, we're choosing them from the population with a certain probability, right? And if you get people in the 115 or the 85, going back to my previous example, that's going to be a low probability that you're going to find those groups of people. Probability will also help us determine how likely our sample data are from the population of interest. How likely is it, for example, that we obtained our sample mean from all possible sample means? It could be obtained from the samples from our population of interest. Our accuracy in determining the population's average score may differ with each sample we select, right? And of course, our goal is to reduce sampling error as much as possible and increase our sample size as much as possible. And that way, that's going to be less noise, if you will, and we can more reliably say, and it'll make our statistics easier, as you'll see, to reliably say that your the results that you found in your experimental group, for example, the caffeine, were actually effective. Sampling techniques. So the book next talks about different types of sampling techniques, which I think are really effective in terms of experimental design, right? And how to reduce sampling error and also sort of obtain enough participants in your study. The way a researcher samples from a population can influence the amount of sampling error present in their data. The closer the sample data come to the data that exists in the whole population, of course, the less sampling error you'll have. You want to, of course, balance the desire excuse me, to reduce sampling error and select a representative sample with the practical limits of selecting individuals from very large populations. Obviously, we talked about that, right? You can't get everyone from the population, so you got to balance that. Generally, two different types of sampling techniques, probability samples and convenience samples, and they really list as they kind of are described, right? This has to do with probability, and this is more, you know, how convenient are they? Who can we get to join our, you know, Milgram experiment or whatever that we're shocking people or pretending to shock people or something like that. Probability samples are chosen such that everyone in the population has a specific predetermined chance of being selected at random. Keyword there. More likely to be representative of the population, and the sampling error will typically be smaller than a convenience sample, where samples are chosen from the population based on their convenience of their availability. Also known as purposive samples, so those are interchangeable words. Easier to select and are often used in cases where researchers want to learn about a very large population. And so then the book breaks it down in terms of probability samples into a couple different types. Simple random samples. All individuals in the population have an equal chance of being selected for the sample. The chance of any one person being selected is 1 divided by the total number of people. So if you have 20,000 students at your college and you take a sample of 1,000 students, the chance of them being chosen is 5%. If it was one student, it'd be like 0.00005. I think that's right. Anyway, you get the drift there. We use the random selection process to create a representative sample. these simple random samples require a researcher to first identify all the individuals in the population in order to randomly select some of them, right? An example, randomly dialing a phone number to call the individual selected. However, this process might still provide a sample that is biased, right, in some way with more individuals. For example, from a certain geographic area, racial or ethnic group. You are randomly selecting them, right? But even with that random selection, you may have more people on the West Coast, more people on the East Coast if you're trying to sample people from throughout the United States, for example, or throughout the 50 states. Samples chosen randomly from clusters. So clusters is a way to solve this problem that I was just talking about, where if you wanted to have representative people from all the states, you could do this in a cluster sample. Or in this example, instead of polling all the students from throughout the United States, you're going to want to make sure that you poll students from not just the big colleges, or not just from the West Coast or the Pac-10 or something like that, but you want to poll them from all of the different colleges, or all the different zones, if you will. So you're going to choose clusters and then randomly select them from the cluster. So you're going to make sure that you get bits of data from each area, as opposed to the previous example where you may be missing some of those areas. Okay? So in the example here, it says it does reduce bias to oversampling from a group or cluster within the population. And then you also have stratified random samples. So suppose you have a category like male, female, and you wanted to know something of a topic of interest. And the fact that, if you just did random sampling or cluster sampling, you might accidentally have an even amount of males and females, or not accidentally, it might distribute that way, when in fact you don't want that, because there are more perhaps females in the colleges, 60% versus 40% males. And you want to reflect that, because you don't want to have the male-female variable affect your study. So you want it to properly reflect the population, and you can do that through a stratified random sample. They allow researchers to control the percentage of their sample that falls into a specific category, like male, female here, because obviously the women are taking over college, right? And showing that, as I tell my daughter, that's because women are smarter than men. And so that's why they're graduating from college more, right? Woo woo, gotta support those women, right, men? In any case, going back to the example, they help reduce bias by keeping the representation of different population characteristics equal across the sample and the population. And then convenient samples, obviously not very strong, right? And you have volunteer samples, sample chosen for population such that available individuals are chosen based on who volunteers. So it could be like studying people in San Francisco, and you study people that are at a bus stop, for example, or people that are just willing to come in your study that, because you have free pizza or something like that. And so that was me in a lot of college studies. That's where I got a good example of that. But obviously, it would test people who are hungry or don't have money and want free pizza, right? And then you have quota sample, sample chosen from the population such that available individuals are chosen with equivalent proportions of individuals for a specific characteristic in the population and sample. Again, it's a convenient sample, but you're trying to choose a specific proportion, similar to the stratified random sample, right? Where you would find a certain proportion of what you wanted, stuff like that. They're much easier to obtain than probability samples. They can sacrifice some internal validity of the study due to an increase in sampling error, obviously, and they might reduce the researcher's ability to generalize their results to the population of interest due to the possibility of a non-representative sample, i.e. just people who wanted to partake in your study, and that might significantly change the results in some way. This is kind of a cool overview of the different techniques of sampling right here, and some really cool overviews of the advantages and disadvantages. With simple random, remember each member has an equal chance of probability of being selected from the population, and it reduces sampling error by choosing all members from the population to best represent the population, but it's difficult to ensure that each member of a very large population can be chosen in the sample, and that's why you use cluster random sampling. And the cluster sampling makes it easier to choose members randomly from smaller clusters to better represent the population. And that's the idea of making sure that you get all different segments of the United States if you're looking at college students. Remember we talked about that. But if you don't have the correct clusters, if you ignore a cluster, then they're obviously going to be left out. So, but that can be addressed. Stratified random, you're going to use a proportion, right? Or you can use a cluster and then also make it proportion within each sample, right? So you can use a cluster and look at all the different colleges within the state, but then each sample within those is going to reflect the male-female difference in terms of their population numbers. And then convenience sample. And then in this you reduce bias, of course, because they're being now reflective of the population. And it can be difficult, similar to random sampling, to ensure that they're all there. That's why you could use a combo of both, right? And then the convenience, it's easier to obtain, and that's the benefit, but not too many benefits in terms of that because of selection bias. All people that love pizza, but who doesn't love pizza, right? Distribution of sample means, intro. Very important concept here, this distribution of sample means, as I'll talk about in a sec. First part of the section of that chapter talks about connecting samples to the population. One way to minimize sampling error is to have a sample size that's big enough, right? And that way you reduce sampling error, but small enough that we'll be able to test that sample in our study. And you have the case one, largest sample possible would be the entire population, which you'll have no sampling error. Remember, it'll get to those 100 cases. But of course, it's too large mostly to include in your study. And then case two would be the smallest sample possible, would be one person. And you would, of course, maximize your sampling error because who knows where they're going to show up on that dart, right? They could be close to the middle, they could be farther away. Oh, that's a good transition, right? With the dart, right? And you can see they also talk about this new concept called variability. And variability is very important we'll talk about it in terms of variance and standard deviation, stuff like that, in future chapters. For now, just know variability in scores in the sample also increases sampling error. The more variability in sample data means they're less reliable to estimate the population data. And as you can see here, they look a little more like the population data, right? If the population data hovers towards the middle, and these guys don't really look like it. But as you can see, if we have more darts, we'll start to pop in some out here, and more will fill in here. And then with this, more and more will fill in here with each one because they have a higher probability of you finding them. Because things tend to hover in a symmetrical distribution towards the mean, towards the center, as you've seen in a lot of the data and we've talked about. We'll talk about that in a future chapter called the central limit theorem. So it's important to conduct multiple studies to test different samples from the population, right? You could choose someone from the 115, the Mensa bus loads, right? And so just as the scores within a sample can differ from one another, the average scores we get from different samples can also differ from one another. And we do not assume that we have proven something about a behavior from one single study, right? Because that could just have been the Mensa group showed up and it wasn't caffeine. And then the distribution of sample means, super important concept. It's a theoretical concept, or theoretical idea. It's defined as the distribution of all possible sample means for all possible samples of a particular size from a population. Again, it's a theoretical concept. It provides the basis for being able to compare results from your experiment to a control group. For example, the caffeine group we use as example. And for example, to be able to say with a certain statistical certainty that the data that you find supports your hypothesis. For example, if only 2% of all the sample means and the distribution of sample means hover around the score of 115, right, like we talked about earlier, then we can say that there is a 2% chance that our mean score of 115 from our experimental group is due to chance. and that we are 98% sure that the change is due to the result of caffeine. So as you can see, very small instances, right, and all the distribution of sample means. But using inferential statistics, what we're going to say is if we get the score of 115, there's a 2% chance that that was due to what? Air. So we can then say with 98% surety that the caffeine is doing something to help with memory, right? It's supporting our hypothesis. And so that's the crux of kind of the distribution of sample means, as we'll get into inferential statistics, is taking a look at probability and where if you have a symmetrical distribution similar to the population mean, if you have a really high score and it's different from the population mean, then you'll be able to use probability and inferential statistics to say with a certain amount of surety, right, in this case 2% surety or 98% surety, that the results were due to the experimental intervention of your independent variable and not due to error. But there still is a chance that it's due to error, right? Because in the distribution, you could have all of those Mensa participants on the bus arriving at your area that you're going to research them. So hopefully that makes sense and gives you some little basis and solid understanding for this chapter as well as the future chapters, which start to go into the mean, variability, standard deviation, variance, and z-scores, and ways that you can start to interpret data. For example, I like to use a caffeine study because it just makes it so easy to be able to say, hey, yeah, with a certain amount of statistical surety, the results that I got are different than the control group. Okay, see ya on chapter 4.